So, Bohr and the quantum atom, problems with the Rutherford model. You can write this down. I've already given you the physics lesson, so let's bring up all of the problems. Haley supplied us with the answer to what Rutherford came up with to solve the problem of the protons not flying everywhere, and that was what we call the nuclear strong force. Strong force is what he used. The nuclear strong force has been mapped out in great detail. Scientists know now that it is a special thing that only acts on short distances. Another problem, negatively charged electrons did not crash into the positively charged nucleus, and they should be. They should be giving up energy in form of light. They should be slowing down. They should be spiraling into the nucleus. It doesn't happen. Also, if they were to spiral into the nucleus, they should be giving off a continuous spectrum. They should be giving off all the colors of the rainbow as that takes place, and it doesn't happen. Before we continue on and talk about how Bohr solved the problem, let's define a few things in here, and let's start by defining what a continuous spectrum is. A continuous spectrum is essentially the colors of the rainbow. It's actually even beyond that. It also involves colors that we cannot see, the entire electromagnetic spectrum. So a continuous spectrum is the pattern of color observed when white light is passed through a prism or a spectroscope. And we'll talk a little bit more about spectroscopes and prisms in a moment. And essentially, a prism can separate light out into its colors using something called refraction. And when you take that white light and spread out, you get a continuous spectrum. All right? Now, that's not what scientists observed. When scientists, even before they were talking about protons, neutrons, and electrons, which is in the like 1900 and a little bit later, like 1910, 1915. Even before that, scientists were looking at the light that was coming off of gases, that was coming from substances that were electrified. I'll show you some examples in a moment. Let's talk a little bit first then about what a line spectrum is. A line spectrum is different than a continuous spectrum. A line spectrum is a pattern of distinct lines, each of which corresponds to a light of a distinct wavelength or color, produced when light consisting of only a few distinct wavelengths passes through a prism or spectroscope. You've seen, like I said last year, hopefully, that if we take a prism, it's usually a triangular prism, right, that is, elongated. You take some white light in that prism, and as the light goes through the prism, the light spreads out into a rainbow of colors, and it doesn't have to be a glass prism that does this. A raindrop works just as fine. There's another way in which we can generate rainbows or separate light out into its color, and that's using something called the diffraction. What I want you to do right now, close one eye, if you have the ability to wink. If not, you can use your hand to close that eye. And take a look at the lamps and at the windows and all that good stuff. Now, a diffraction grating is different than a prism, right? Obviously, there's not a big hunk of glass sitting there. So diffraction grating works a little differently than a prism. But you'll notice it still creates colors. The way it creates colors has to do with the way it's built. Essentially, that's a little piece of cellophane plastic. And what they've done on the cellophane plastic is they've put a bunch of little lines very close together, all right? And if you take grade 12 university physics, and you should because it's good for your health, it makes you a healthier, better person. Anyway, you will learn how a diffraction grating works and how when light passes through slits, tiny little slits, it also spreads out, very much like it does in the prism, but it actually uses a completely different method. But it spreads the light out. Let me show you kind of how it spreads it out. Now, that particular device is doing exactly what it's doing with the white light, except a laser beam has only one color, all right? One color. And because it has only one color, it's separating that color. Now notice how it's separating it not just left and right, but up and down, which is why when you guys, with the cool ones, look at the light, you see colors going everywhere. And that's because that diffraction grating not only has horizontal lines, but it's got vertical lines as well. Before we move on and talk about how a diffraction grating is important, diffraction gratings will always have repeating patterns, all right? And diffraction gratings simply spread light. So what were scientists doing with their prisms and diffraction gratings? Well, they weren't looking at lasers, but they were looking at the light that was coming off of electrified gases. And they were looking at the light that was coming from the gases through a diffraction grating or prism. Each gas, scientists discovered, had its own distinct color. Each element that was in the gaseous state had its own distinct pattern out. So it was this line spectrum that really got scientists thinking, how do we explain this? So what did Bohr propose, and how then did it take care of some of the problems like line spectra and the problems of Rutherford's atom? Now that first statement, nothing is new. Bohr's model stated that electrons could only exist in discrete energy levels, or orbits, we call them. Orbits actually comes from the idea that Rutherford proposed, that they had to be moving, but we now know that if they're moving, they should be giving off light. So energy levels is better, and actually shells are even better. But we still use the term orbit. Now in the next statement, there's the term, in quotes there, the energy of the electron is said to be quantized. And that's the word that is used when we talk about this idea of quantum mechanics. The word quanta simply means a little discrete piece, all right? Scientists before 1900 felt that energy was continuous. You could have any value for energy, that you could have 1.2 joules or 1.21 joules or 1.22 joules. There was no break in the values of energy that you could have. You could have whatever energy that you needed. The atomic theory is actually a type of quantum theory, because instead of having matter being, spread out like you could a bunch of plasticine or something, matter is made up of tiny discrete pieces. That's a quantum theory. It involves little quanta. We even did the same with electricity. Scientists thought that electricity just flowed like a river through a wire, but then Thomson and some other guys discovered the electron, the smallest piece of electricity. That's a quantum theory. It states that you can only have discrete tiny pieces of electricity. This guy, Max Planck, in 1900, found that light was actually made up of tiny discrete pieces, quanta. We call them photons now. And all Bohr did was to say, okay, well, if all of these other things can be made up of little tiny pieces, then maybe the energy that an electron can have can only be made up of tiny discrete pieces of energy. In other words, the electron can exist here, or it can exist here in the next shell, but it can't exist in between. There's only discrete places that it can exist. And that's where our energy levels come from. So all Bohr did was apply this idea of little chunks to the energy found in an atom. In the mathematics that he used to explain this, because this was all explained mathematically, very mathematical. He's applying mathematical ideas that were applied to the light and to the electrons and to all this stuff. He's doing all kinds of crazy math. And in the end, when he's done doing the math, the answer to the problem produces these energy levels. In the math he was doing, there was a variable called n, and that variable essentially numbered the energy levels, which you call the first energy level, or the first orbit, and the second energy level, the second orbit. In his theory, he named it the principal quantum number because it's the main number that defines the orbit itself. How big it is, how fast the electrons would be moving if they were, because they really can't, but he could calculate that. So all this stuff came from this. So we call it energy level 1, energy level 2, etc., etc. They were given symbols at first. The first energy level was given K, called the K shell. The second one L, M, N, etc. So he quantized the energy, put them in shells. The principal quantum number numbers the shells, 1, 2, 3, 4, etc. And we can also use K, L, M, etc., etc. Okay. That's the essential part of Bohr's theory. Here's some of the assumptions that he had to make in order to come up with that theory. And these were the kind of the new ideas that he needed in order to explain the atom, in order to kind of fix the issues with classical physics. Classical physics wasn't able to explain this, so he had to come up with some new rules. The first rule he had to state: an electron doesn't lose energy when it's in an energy level. Even though classical physics says if it's in an orbit, it should be losing energy, Bohr said, we don't see it doing that, so it can't be happening. It's able to exist in an energy level without giving its energy up. It's like it's in a parked state. He actually used the term stationary state, as if it's kind of just hanging out there. Even though, according to classical physics, it can't. It should crash, but it does. And you can literally think of the electron as if it's kind of just hanging out there on the orbit, just hanging out there. Higher energy levels are farther from the nucleus. That's really nothing new. Higher levels of gravitational energy are farther from the surface of the Earth. You want to go to a higher energy position on the surface of the Earth? Climb Mount Everest, you're on the highest energy position, right? If you slip, you will fall down to a lower position, all right? Electrons will do the same thing. If an electron is in a higher position, it can fall down to a lower position. So the second rule isn't really anything earth-shattering because it's the same as gravitational energy. If you're at a further orbit, you're further from the nucleus. An electron cannot exist between orbits, but can jump to orbits of higher and lower energy. Now that's the first kind of idea of the weirdness of quantum mechanics. Quantum mechanics, when you go on to chemistry and study quantum mechanics, the rules that govern the tiny, like electrons and atoms, are strange rules. Let me give you an example of what that number 3 stands for. Bohr said you can have an electron here at 1, or you can have the electron here at 2, and it can jump between 1 and 2, but it can't exist between 1 and 2. That would be the same as you climbing the steps to your bedroom at night, climbing each step, but as you go from step 1 to step 2, you don't exist between the 2 steps. It would be like you going from step 1 and poof, poof, step 2, poof, step 3. Obviously that doesn't happen with us, but that's because the physics of the large world is different than the physics of this tiny world. The quantum mechanics rules that. So that's a strange, strange thing. So number 4. So what have we got so far? We got energy levels. We've got further ones. Higher energy levels are further away. And we've also got that they can jump from one energy level to another, but they can't exist in between. That's the fun part. And now some terms. Electrons typically exist closest to the nucleus in the ground state. And that's just like our gravitational analogy. Human beings typically exist closest to the surface of the Earth on the ground, right? If energy is added, the electron can jump to a higher orbit and that's called an excited state. We say that the atom is excited. An excited electron will eventually fall back down to the ground state, but as the electron drops back down to lower orbits, they release light, and that's where the line spectrum comes from. When an electron falls down, it gives off a burst of light. That's the only way it can release energy. Okay? The size of the jump determines what color it is. So this explains now our line spectrum. If an electron, say in hydrogen, goes from the third to the second energy level, it gives off a red line. Red is low energy. That's just a little tiny jump. But if it goes from the fourth down to the second, it gives off a blue line. That's a bigger jump. That's more energy. If it goes from the fifth down to the second, that's an even higher energy blue, like a violet, a bigger energy jump. If it goes from the sixth down to the two, it's this last line here. You might ask, what happens if it falls down to the one? If it falls down to the one, the jump is so big, it gives off ultraviolet light that we can't see because the jump is so big, it's a higher energy value. So for each different size jump, we get a different color. You get a whole bunch of hydrogen in a tube and you zap it with electricity. The electrons get all excited in a whole bunch of atoms and they fall back down at random times. One falls down now, the other one falls down a little later. So they keep jumping up and falling back down. Every time they fall down, a little bit of light comes out, hits you in the eye. Some of them are falling from the third to the second. Some are falling from the fourth to the second, fifth to the second. So all the time as they're jumping up and down, all these colors are coming out, depending on which one is jumping which. All the colors hit your eye at the same time, and your brain adds those colors up to perceive the color orange for neon, even though you might have saw some red and some green and no blue. So you're seeing all the electron jumps simultaneously. How does an electron get energy? An electron can get energy and go higher up three main different ways. All right. You can use electricity. I put it away. You can use electricity. That's exactly what I'm doing when I'm zapping these gases. What's happening is a big stream of electrons is flying through the gas, and every once in a while, one of these electrons that come from the Tesla coil runs into an electron that's in an atom. And what does it do? Boom! Kicks it up to a higher state. And then it keeps on, the other one just keeps on going. Zapping a gas excites them by running electrons into other electrons. You can also get electrons to be excited by heat. If you've ever, if you've got one of those old stoves, with the spirally things, the electric ones, you turn on, it starts to glow red, or if you've cut any steel with a torch and it's glowing red, what happens there is adjacent atoms are vibrating against each other so much they literally bump up against each other, and if there's enough energy, the physical bump can cause an electron to jump up. And then it falls back down and gives off some light. All right? So that's number two. You can heat or you can zap it. Number three is you can use light itself. If you were to shine a red beam of light, that exact color, on hydrogen, that would be the exact opposite of when it falls back down, and it'll absorb that light and jump back up. And then it'll fall back down and spit the light back out. But if you could shine that color light onto hydrogen, you could get the electrons to jump up. They'd have to be the perfect color. It's got to be the exact color. If you didn't shine that exact color on it, nothing would happen. It would be like a failed kick. It would result in the electron maybe ending up halfway, but that's against the rules. So it stays where it is, and the light keeps on going. So you've got to hit it with exactly the right color of light to get the electron to jump up. So here's an indication of the three different ways in which you can do that. Here, this is in a Bunsen burner flame. We're going to be doing this in our experiment. We're going to take some atoms that are soaked onto a stick. We're going to put the stick in the flame, and it's going to glow. We're going to make the electrons jump with the heat. This is an electric discharge tube. This little graphic here represents a Tesla coil. It's actually a couple of coils. It's a transformer. You don't have to worry about it. But here's one of those tubes, and we're going to zap it with electricity. We're going to look at that too. This, I have no idea what this is representing. Oh, it's an arc lamp. We can use an arc lamp. Oh, that arc lamp is supplying light, right? So this is the one where if you shone light on it, you could get it to jump. An arc lamp is an old piece of equipment. You can tell this is not my newest poster that I have in the room. Stars, all right, give off light by the electrons jumping up and down. Scientists can actually determine what elements exist in stars by separating the light out into their lines and then looking at that great mixture of lines and separating them out and then saying, hey, there's some sodium on the surface of the sun. There's some other elements there. Okay. One last little thing here to go along with Bohr's theory. And that has to do with the number of electrons in each of the orbits. Remember I said that Bohr didn't just sit there one evening and start drawing circles on a page and invent the Bohr diagram, right? That's the simplest representation of what he came up with. He did mathematics. That's what physicists do. Pages and pages of math. They start with some ideas, and in the end, the mathematics comes up with answers that then have physical meaning. And the orbits are the answers to these big pages of equations. And another answer that came out of all of these equations was an equation that provided the number of electrons that could be in each orbit. And that equation is 2n squared. So the number of electrons in each orbit is 2n squared. This came out of the mathematics. He didn't make it up. He did a whole bunch of math, and this is what came out. So we can do this. How about if n is equal to 1, the first energy level, how many electrons can fit in the first energy level according to his mathematics here? Therefore, number of electrons equals 2. And then I'm going to put a 1 in here. And what's my answer? Sorry? 2. 1 squared is 1, times 2 is 2. You guys knew that, right? You guys have been putting 2 dots in that first orbit since grade 9, I would hope. Right? Yes? No? Sounds good? Let's look at the second energy level. If n, what, you're going to stop now? If n is equal to 2, number of electrons, 2 squared. What's the answer? Yep, 8. 2 squared is 4, times 2, 8. And at this point, you guys are all going, yeah, man, this is good stuff. 2, 8, right? 2 and 8. N equals 3. I'll put it over here. N equals 3. Therefore, the number of electrons equals 2, 3 squared. How many electrons should go in the third energy level? Yep. Yeah, the mathematics gives us 18. 18 electrons. And at this point, you're going, wait a minute. For years, we've been drawing 2, 8, 8. Where's the 18 coming from? And this is where it gets a little complex. It turns out that in each of these energy levels, there's actually sublevels. There's subshells that exist within the shells. And when you get to higher ones, subshells begin to overlap. And then the numbering gets really goofy. In actual fact, right here in the transition metals, okay, these right here, their electrons are actually going into the third orbit, even though they're in the fourth line. Which means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And that's where the shape of the periodic table comes from. It comes from the orbits and how the electrons go into them. How about 4? N equals 4. We'll stop at 4 here for a minute. N equals 4. And therefore, the number of electrons, 2, 4 squared. What is that? Yep, 32. 32 electrons. And now you're going, what the heck, 32 all the way across that thing? That's crazy. You'll never get to 32. But again, like I said, there's an overlap. And it turns out that these guys in here are actually going into the fourth. So if I count across, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually, let's go down to this guy here. Well, no, let's do it this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Now you might say, oh, Mr. Sanders, what about that guy? That makes 33. These two actually go in this space here, so they don't even count. So all the way across, including these guys down here, 32 comes from that number right there. The shape of our periodic table is not because of periodic trends like Mendeleev thought, but it has everything to do with the orbits and the way the electrons go into them. You don't need to know this stuff that I just mentioned, but you will next year. We'll explain the periodic table completely next year in great detail. All right? And that's where our funny numbers come from. As far as you're concerned, if I'm having you draw Bohr diagrams, 2, 8, 8, and then we stop there because it gets confusing. You don't know enough to actually draw the pictures for these guys. I've seen websites where they just put a whole bunch of dots around them. Wrong. That's not even close to the way we look at the atom. So we stop right there because I need to teach you more quantum mechanics before you can learn more about this. But that's not for this course. Okay, one last little place, and then it's a perfect place to stop here. One last little statement. I've already made this statement orally. I'm just getting you to write it down. Each element has different sized orbits, and therefore its own unique pattern of colors. This addresses why all the lines aren't the same. You might think if they've all got the same orbits, each atom, then why aren't all the colors the same? Why don't all atoms look exactly the same color? More protons pulls the orbits in. There's still a fundamental attraction between the electrons and the protons. That's what keeps them in the orbits. As you go from something like hydrogen to helium, each time you move to the next one, you add a proton to the nucleus. That pulls the electron orbits in a little closer. So the orbits for lithium, its first orbit is closer to the nucleus than hydrogen's first orbit because it has more protons and it pulls it closer. Which means when lithium's electrons jump, they make different size jumps. And each size jump gives off its own color, so each element has its unique set of colors because all of their orbits are of different size. And that's very important. That's why when we look at neon being zapped, it's orange, but when we look at another gas, and I can't think of any right now, sodium, if I had a sodium vapor tube, it's very yellow because of the different sized jumps. And because each element has its own size jumps, the line spectrum is a characteristic property. We say it's an intrinsic property. We can use those properties to identify elements. If we gave, and you're going to do that in the experiment. We're going to give you a tube there. It's going to be an unknown. We're not going to have it labeled. You're going to look at the colors, and then you're going to compare it to some other ones that you've already seen, or you can compare it to something like this, and you should be able to identify what that element is in that thing by its colors. All right? And that's all thanks to the Bohr theory with electrons jumping up and down.